study about the harmonically excited single degree of freedom systems, and in this module there will be 4 lectures. In the first lecture we will study about the force harmonic vibration magnification factor using graphical method. In the second lecture we will study about the steady state response using alternative approach like solving the differential equation and Laplace transform method, and we will study about the superposition principles also. In third lecture we will study about the rotating unbalance and wheeling up shaft. In the fourth lecture we will study about the vibration isolation and transmissibility. In the previous lectures you know about the free vibration of single degree of freedom systems. Also you have studied about how to find the equation motion of a single degree of freedom system. So, let us take a simple spring mass damper system. In this simple spring mass damper system, which is the model of most of the systems, you can write the mass equal to m, spring stiffness equal to k, and c is the damping. It is subjected to a force F equal to F0 sin omega t. So, this simple model can be a model of a IC engine or reciprocating engine. In case of a reciprocating engine, you know that the unbalanced force, always there is the presence of a unbalanced force, and so this is a reciprocating engine, this is the crank and this is the connecting rod and this is the piston, and when due to this reciprocating part always there presents a unbalanced force in this, and due to that unbalanced force it will be subjected to this base or the support will be subjected to some motion. Also you may consider a vehicle moving on a rough surface or moving on the road. So, the tire of the vehicle will be subjected to a force due to the road undulation. Also you may consider a robotic arm. In case of a robotic arm, so this is a simple robotic arm, 1 link or 2 link robotic arm. So, this is the end effector of the robotic arm, and this is a single link, or the joints are supplied with motors. So, which rotate these links. So, we are applying some torque or force to these joints. In case of a revolute type of robotic manipulator, you are supplying the torque, and in case of a Cartesian type of manipulator, we are giving the force. So, in case of a Cartesian type of manipulator, so this is a simple schematic diagram of a Cartesian manipulator. So, it is translating in this direction, and this is a revolute type of manipulator in which you are applying torque. So, in case of Cartesian manipulator you have applied force F. So, in some cases we are applying the force to the system, and in some cases like in case of the reciprocating engine or in a vehicle moving on the road. So, some force is transmitted to the system itself. So, due to the transmission of this force or due to these forces, the system is subjected to forcing. So, this force may be of different types. So, this force can be of many different types. So, it may be periodic or it may not be periodic. So, periodic or it may not be periodic. So, when it is not periodic, it may be a fixed force you are applying, fixed amplitude of force you are applying, or you are applying some force which is random force. So, in case of random force, that is in case of a earthquake, the buildings will be subjected to some force which are equivalent to the random force, and in case of fixed force you are applying a constant force to the system, and in case of periodic force you are applying a force which may be harmonic or may not be harmonic. So, this periodic force may be harmonic. So, in case of harmonic it will be either similar to a sine curve or a cosine curve, and in case of non harmonic periodic it may be triangular, or it may be rectangular, or it may be of any shape. So, when the system is subjected to harmonically excited force, that is this force equal to f0 sin omega t or the force equal to f0 cos omega t. So, we can find the response of the system, and when it is periodic, but not harmonic, like in this case of this triangular wave, we can apply the Fourier series to convert that thing to this harmonically excited one. So, we can convert this triangular wave by applying Fourier series to some terms containing sine and some terms containing cos, and we can write the resulting force equal to, so summation, so it will be A0 plus A1 summation AI cos I omega t omega I t plus summation BI sin cos omega I t cos omega I t plus summation I equal to BI sin omega I t. So, we can convert this force, this periodic force, but when they are not harmonic, we can convert them to the harmonic force by use of Fourier series. So, in case of the spring mass damper system, so this force, we are writing this force equal to f0 sin omega t. For simplicity, we have taken is single term f0 sin omega t. One may take a force which may be equal to f1 sin omega 1 t plus f2 sin omega 2 t, or summation of multiple terms, or one may take some other type of forces also. So, in all these, in most of the cases or the most of the systems, for simplicity in analysis, we are converting that thing to single degree of freedom system, or we are representing that thing by a single spring and spring mass damper system. So, most of the systems can be reduced to this form. So, we are studying for the simplicity this simple system, this simple spring mass damper system. So, today I will tell you about the graphical method to solve this equation motion. So, previously you have studied how to derive this equation motion. To derive the equation motion, so you have equation motion. So, either you have used energy principle or you have used inertial principle or energy principle. In case of inertial principle, so you have used either Newton's method or you have used D'Alembert principle. Both the methods are same. This D'Alembert principle convert a dynamic system to an equivalent static system by introducing the inertia force on the system. So, if you have a system, let us consider this mass, it is subjected to a force F. So, when this force is applied to this mass, so it will have a acceleration. So, according to Newton's second law, you can write F equal to ma, but according to D'Alembert principle, so you are converting the system to an equivalent static system by applying a inertia force, which this inertia force is acting in the direction opposite to the direction of acceleration, and its magnitude is mass into acceleration. So, this is the inertia force acting on the system. So, according to D'Alembert principle, this F minus m a equal to 0. So, summation, so this m minus m a is considered as the inertia force. So, summation of all the forces equal to 0, which gives the equilibrium conditions of a static system. So, by applying D'Alembert principle, you can convert this dynamic system to an equivalent static system, and by using Newton's method also you can derive the equation motion. And Also you can derive this equation motion by applying this energy principle. In case of energy principle, you know the Lagrange method, or you also know about the Hamilton's principle. Generally, Hamilton's principle is used for the continuous system, and this Lagrange method is used for multi degree of freedom systems. In case of Lagrange method, we are defining a Lagrangian L that is equal to T minus V, where T is the kinetic energy of the system and V is the potential energy of the system, and we can write the Lagrange equation by this. So, d by dt of del L by del q k dot minus del L by del q k plus del d by del q k dot equal to q k. So, here this d is the dissipation energy and L equal to T minus V, that is difference between the kinetic energy minus potential energy. So, by knowing the kinetic energy, potential energy and dissipation energy of a system, one can find the equation motion by using this Lagrange method. Here q k is the generalized coordinate and this capital Q k is the generalized force and the small q k is the generalized coordinates of the system. Similarly, using Hamilton principle, generally Hamilton principle is applied to a conservative system. So, for some non-conservative system or when some forces are acting on the system, one may use extended Hamilton principle. So, one may use extended Hamilton principle. So, extended Hamilton principle can be given by, so it is T 1 to T 2, T 1 to T 2 del of del L plus del W N C. So, it can be given by del L plus del W N C dt equal to 0 and q k at T 1 equal to q k at T 2, or del q k at T 1 equal to del q k at T 2 equal to 0. So, using extended Hamilton principle, so this is extended Hamilton principle and this is the Lagrange principle. So, using extended Hamilton principle also you can derive this equation motion. So, already you know how to derive these equations motion. So, for a single degree of freedom system and for this simple spring mass damper system, you have so for this simple spring mass damper system, already you have derived the equation motion and that equation motion can be written as, so let this has a displacement x. So, when it is subjected to a force F0 sin omega t, so the equation motion, so this is k and this is c. So, the equation motion is given by mx double dot plus kx plus cx dot equal to f sin omega t. So, here by drawing the free body diagram, one can find this equation motion. So, when this body is moving downward with x, so the spring will be stressed downward and so it will exert a force in upward direction and that force is proportional to the displacement. So, that force is given by kx, and this damper also will be subjected to a force that is equal to Cx dot, and that force is also opposite to the direction of motion. So, this is equal to Cx dot, and the inertia force is opposite to the direction of acceleration. So, this inertia force can be given by mass into acceleration of the system, but it acts in the direction opposite to the direction of acceleration. So, it is given by m x double dot, mass into acceleration. X double dot is the acceleration, x dot is the velocity and x is the displacement from the equilibrium position, and so all these forces will be equal to F0 sin omega t. This is the externally applied force. So, the externally applied force equal to the spring force kx and damping force Ex dot and the inertia force mx double dot. So, by equating these forces, so one can write the equation motion of the system equal to mx double dot plus kx plus cx dot equal to f sin omega t. Now, I will tell you a very simple method to simple graphical method to solve this equation motion. Already you know, for a similar differential equation motion, the solution will be in the form of x will be equal to x sin. So, you know, so x will be in the form of x sin omega t minus phi. So, where x is the amplitude of the response and phi is the phase angle. So, you may note that the frequency of this external forcing and the frequency of the response are same. So, I can draw a very simple force polygon to find the amplitude and phase. So, let me draw this force polygon, let me take a reference line. So, this is the reference line. The external force, you may note that this external force is at an angle omega t from this reference line. So, I am just plotting only the magnitude of all the forces. So, the spring force I can represent by, so spring force is k x small x. So, this magnitude will be k capital X and I can draw that force. So, this is k into x. So, this is k x force and this damping force will be c omega x cos omega t. So, cos omega t minus phi. So, it will be at an angle 90 degree to the spring force. So, this angle is 90 and its magnitude equal to c omega x. Similarly, the inertia force mx double dot. So, this will be equal to minus m omega square x. So, minus m omega square x. So, this is opposite to the direction of the spring force and it will act in this direction. So, it will be parallel to this line and its magnitude equal to m omega square x, and this closing side will be the applied force. So, this is the applied force that is equal to F 0. So, F 0 will be equal to the vector sum of k x c omega x and m omega square x. Now, to find this x, I can draw a line parallel to this here. So, I have drawn a line parallel to this. So, this F 0 will be, so now this F 0 is acting at an angle omega 2. So, this is the reference line. So, from this reference line F 0 is at an angle omega t. So, this angle is omega t and so this angle I can take this inside angle between this force and this k x line equal to phi. So, this angle equal to omega t minus phi. So, as this angle is omega t minus phi. So, this x response x is at an angle omega t minus phi with the reference line. So, this force is at an angle omega t with the reference line, the displacement. So, this is the displacement line along this displacement. So, it is at an angle omega t minus phi. So, now I have to find the magnitude of this x. So, from this triangle one may find that F 0 will be equal to this square plus this square and this part equal to k x minus m omega square x and this is c omega x. So, this square plus this square will be equal to this F 0 square. So, I can write this equation in this form. So, k x minus m omega square x whole square plus c omega x whole square equal to F 0 square. So, from this one can find this x, one can take, so this is capital X. So, one can take x common. So, it is equal to x square I can write, or x can be written as x will be equal to F 0 by square root of k minus m omega square whole square plus c omega whole square. So, now one can divide k in both numerator and denominator and write this equation in this form. So, this will be equal to f 0 by k. So, this will be equal to 1 minus m by k. So, this m by k omega square whole square plus c by k omega whole square. So, already you know that m by k root over k by m. So, omega n square equal to k by m, and also you know that c by m equal to 2 zeta omega n. So, the c by k you can find. So, c by k will be equal to, so c by k will be equal to c by m into m by k. So, this is equal to c by m, I can write equal to 2 zeta omega n, and this m by k equal to, already m by k will be equal to 1 by omega n square. So, it is equal to omega n square. So, this omega n cancel. So, this is equal to 2 zeta by omega n. So, the c by k term I can write equal to 2 zeta by omega n. So, this term become 2 zeta omega by omega n whole square, and this becomes omega by omega n whole square. Now, this f 0 by k. So, this is the spring has a stiffness k and it is subjected to a force f 0. So, it will have a displacement x 0. So, this is the static displacement of the spring, or this is the static displacement of the system with a spring constant k. So, when a magnitude force of magnitude f 0 act on the system. So, it will have a displacement of x 0. So, this f 0 by k can be called as the static displacement of the system. So, this displacement x can be given by, so this x can be given by, this is, or x by x 0 can be given by 1 by root over 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. So, I can write this omega by omega n equal to r frequency ratio. So, this equation I can write equal to, so this will be equal to 1 by root over 1 minus r square whole square plus 2 zeta r whole square. So, now I have to find. So, from this you know that this dynamic amplitude or this amplitude of response equal to f 0 by k or x 0 by root over 1 minus r square whole square plus 2 zeta r whole square. So, this is an important equation which you should remember. Now, I have to find the phase angle. So, this phase angle phi also can be obtained from this triangle. So, in this triangle this phi tan phi equal to, so tan phi will be equal to c omega x by k x minus m omega square x. So, I can write tan phi equal to, so tan phi equal to c omega x by k minus m omega square x. So, cancelling this x, it is equal to c omega by k minus m omega square. So, again now dividing this k in the numerator and denominator, I can write this equal to, so this tan phi I can write equal to c omega by 1 minus, so this is equal to c omega by k minus m omega square 1 minus, so this is k minus m omega square. So, I am dividing k. So, this is c by k omega by 1 minus m by k omega square. So, this is c omega by k and 1 minus m by k omega square, and already you know that c by k equal to, already we have derived that c by k equal to 2 zeta. So, this is equal to 2 zeta by omega n. So, this is equal to 2 zeta by omega n. So, this is equal to 2 zeta omega by omega n by 1 minus this m by k equal to k by m equal to omega n square. So, this is equal to omega by omega n whole square, or this thing can be written as 2 zeta r by 1 minus r square. So, we obtained, so for the given system parameter m, k and c. So, we can find the response of the system when it is subjected to a force f0 sin omega t. So, here zeta is the damping factor and omega n is the natural frequency of the system. Natural frequency of the system you know equal to root over k by m, and also you know that your zeta, that is damping ratio, that is equal to damping factor C by critical damping Cc. So, you know this thing from the free vibration analysis of this system. So, using all these system parameters you can find the response of the system. So, this factor x by x0 is known as the magnification factor of the system. X by x0 is known as the magnification factor of the system, and we can plot. So, this is magnification factor. So, one can plot this magnification factor versus the frequency ratio of the system. So, from this equation you can see that when r equal to 0, that is when omega equal to 0. So, this becomes 1 and this becomes, so r equal to 1. So, this becomes 2 zeta. So, this is when r equal to 0. So, this becomes 1 and this part equal to 0. So, this is 1 by 1. So, this becomes 1, and for a undamped system, that is a system without damping, zeta equal to 0. So, this becomes 1 by root over 1 minus r square whole square. So, when zeta equal to 0, this x by x0 tends to infinity when r equal to 1. So, when r equal to 1, this part equal to 0. So, r equal to 1, if you substitute in this equation, 1 minus r square will be equal to 0. So, this x by x0 tends to infinity. So, we can plot this magnification factor versus omega by omega n, and we can, so it can, you can see this curve. So, already I have plotted this. So, this is x by x0 versus omega by omega n. So, when, so for a undamped system, that is zeta equal to 0 at omega equal to omega n, or this ratio equal to 1, the response tends to infinity. Also, you have seen that irrespective of damping, when r equal to 0, this x by x0 equal to 1. So, this x by x0 expression you already know. So, this is equal to x by x0 equal to 1 by root over 1 minus r square whole square plus 2 zeta r whole square. So, from this you just see that when r equal to 0, this becomes 1, and for a undamped system, that is zeta equal to 0. So, this tends to infinity. So, when when omega is very greater than omega n, or when the system is operating at a frequency which is very away from the natural frequency, you can observe that. So, this one term can be neglected with respect to this r square term, then this will, so at that time it will be equal to, so this will be equal to 1 by, so this will be a very large term, this denominator will be a very large term, and this will tends to 0, or this will be a number, very small number you will get, or this x by x0 will be very less. That means, when the system is operating at a frequency away from the natural frequency, this amplitude of response amplitude is very less, and it is less than the static amplitude or static amplitude of the system x0. Also you can observe, this is for a different value of zeta, this magnification factor is plotted. So, this is equal to, this is zeta equal to, this is zeta equal to 0.5. Okay. So, for different value of zeta, the response is being plotted. So, this is zeta equal to 0.25 and this is zeta equal to 0.5, this is zeta equal to 0.7 and this curve is zeta equal to 0.75, this is zeta equal to 0.8 and this curve is plotted for zeta equal to 1. So, you can see that with increase in zeta, that is increasing the value of damping ratio, the maximum amplitude of the system decreases. So, by using this damping, when the response is near this omega 1, so you can decrease the resonant amplitude of the system. And you can observe that for a value that is more than 0.75, the magnification factor is less than 1. So, you can observe that with increase in damping, the response of the system decreases, and also you can observe the maximum peak is occurring towards the left of the value omega equal to omega n. For a undamped system, so you are observing that the maximum amplitude occur at a frequency omega equal to omega n, and for the system with damping, it occurs at a value slightly to the left of the omega n, that is omega slightly less than omega n, you are getting this maximum amplitude, and when omega by omega n is very large, then the response amplitude is very small. Also you can plot the phase angle versus phase angle phi versus this omega by omega n. So, in this case you can observe that for low damping or for a undamped system, the angle phi is almost 180 degree for frequency omega by omega n greater than 1, and for all the systems you can see that for very low value of omega by omega n, this response, this phase angle is near 0. Also irrespective of damping, you can observe that it has a phase angle of phi at omega equal to omega n. So, at omega equal to omega n, so this angle is 90 degree. So, irrespective of value of zeta, all the systems will have a phase angle of 90 degree when omega equal to omega n or omega by omega n equal to 1, phi tends to 90 degree, and when omega by omega n very greater than 1, you may observe that for low damping it tends to 180 degree, and for or with increase in damping this value decreases. So, in this way one can find the magnification factor of the system, and also one can find the phase angle of the system. So, now we should find what is the peak amplitude or peak value of this response, and what is the frequency at which this peak value is obtained. So, already we know, so we can, so let us find the, so let us take this example. So, find, so in this example we have to find the maximum amplitude. So, we have to find the maximum, find the maximum response amplitude of a spring mass damper system. So, in this case already we know that the response can be written as x equal to f 0 by k. So, this is f0 pi k root over 1 minus r square to the power or square plus 2 zeta r whole square. So, this will have a maximum amplitude, this will have a maximum amplitude when this denominator is minimum. So, we have to find, so for what value of r this denominator is minimum. So, for that I can write this, let me take a function f. So, this function f 1 minus r square whole square plus 2 zeta r whole square. So, this should be minimum. To find this minimum value, so I can differentiate this df with respect to r and equate it to 0 and I will find the value of r. So, in this way I can find, so this 1 by r square whole square I can write this equal to 1 plus, so this becomes r fourth and this becomes minus 2 r square plus 4 zeta square r square. So, now df by dr, so I can differentiate this thing. So, this becomes 3. So, if I differentiate this, so I can have r fourth. So, this becomes 4 r cube minus, so this becomes 4 r and differentiating this it will become plus 8 zeta square r. So, this will be equal to 0. So, I can take r common here. So, if I will take r 4 r I can take common. So, if I will take 4 r common, so 4 r into, so this becomes r square minus, so this becomes 1 plus 2 zeta square equal to 0, or I can see that at r equal to 0 or at r square equal to 1 minus 2 zeta square, the response amplitude will be maximum. So, either at r equal to 0. So, when r equal to 0 you have seen that response amplitude equal to 1, and when this becomes, so when r square equal to, so you can find that when r square equal to 1 minus 2 zeta square or r equal to root over 1 minus 2 zeta square, the response amplitude is maximum. So, this is the frequency ratio. So, for this frequency ratio you can find the response to be maximum, or when omega, the frequency of the external excitation equal to 1 minus 2 zeta square time the natural frequency of the system will have a maximum amplitude. Now, to find this response amplitude, maximum response amplitude, I can substitute it in that equation. So, this will be equal to f0 by k or x0 by root over 1 minus r square. For this r I can substitute this value. So, 1 minus square of this. So, this becomes 1 minus 1 plus 2 zeta square whole square plus 2 zeta r. So, for this r I can write root over 1 minus 2 zeta square this whole square. So, in this way I can find, so this is equal to, so this part 1 cancel. So, this is, so this x marks I can write equal to, so this x marks equal to x0, or this x0 I can write equal to f0 by k into 2 zeta root over 1 minus zeta square. So, the maximum response amplitude becomes f0 by k by 2 zeta root over 1 minus zeta square. So, when zeta equal to 0, so this response amplitude tends to infinity. So, we should now let us solve another problem. So, in this problem we will take an air compressor. So, this air compressor has a mass of 100 kg, it is mounted on an elastic foundation. So, this elastic foundation can be modeled as a spring of constant k and a damping c. So, it has been observed that when the harmonic force of amplitude 100 Newton is applied to the compressor, the maximum steady state displacement is found to be 5 mm, which is occurring at a frequency of 300 rpm. So, we have to determine the equivalent stiffness and damping constant of this foundation. So, this compressor we can model it as a single degree of freedom system. with mass m equal to 100 kg, k. So, we have to find this k and c of the system. So, in this case it is given that the maximum steady state displacement is 5 mm. So, this x max is given to be 5 mm and it is occurring at a frequency omega also it is given. So, omega equal to 300 rpm. So, this rpm I can convert it to radian per second by multiplying 2 pi. So, this is 2 pi by 60 I can multiply. So, this becomes 10 radian per second. So, this equal to 10 radian per second. So, I know omega, I know x max. Now, I have to find the response of the I have to find the equivalent stiffness and damping of the system. So, in this case I can find it like this. So, I know this formula x max equal to f 0 by k by 2 zeta root over omega 1 minus zeta square. So, x max equal to f 0 by k 2 zeta root over 1 minus zeta square, and already f 0 is given to be 100 Newton and m is given to be 100 kg and steady state maximum x max is given to be 5 mm. So, the resonant frequency also is given omega r equal to already we have found, that is equal to 10 pi radian per second. So, from this equation I can write that this 5 into 10 to the power minus 3. So, I have to convert this thing to meter. So, 5 into 10 to the power minus 3 equal to f 0, that is 100 by k root 2 zeta into root over 1 minus zeta square. So, this is the thing. Also I know this omega n square equal to, I can use this formula omega n square equal to k by m, and m is known to me. So, this is equal to k by 100, and this r is, I know the relation between r and zeta for maximum amplitude. So, I know r equal to omega by omega n. So, this is equal to root over 1 minus 2 zeta square. Already you know that maximum amplitude will occur at a frequency of root over 1 minus 2 zeta square. So, this omega n is root over k by m and this omega is known to you. So, this is equal to 10 pi by root over k by 100. It is equal to root over 1 minus 2 zeta square. So, you have two equations, and so from this equation and the previous equations also you know this. So, by solving these two equations you can find k, the value of k and zeta. So, the value of k and zeta you can find. So, they are obtained to be, so this k you can find equal to k you can find it is equal to 100.7 kilo Newton per meter, and the equivalent damping C equal to 633.396 Newton second per meter. So, in this case you are using the formula zeta. So, first you can get the value of k and zeta from these two equation. So, from this equation, this is your equation 2 and this is equation 1. So, from these two equation you can find. So, this is 1 minus zeta square. So, this 1 minus zeta square term you can substitute it from this. So, and you can find this zeta value first, and after finding this zeta value you can note that zeta you are getting to be getting it equal to zeta you are getting equal to 0.0998. So, this thing you can obtain. Now, first you square this thing. So, you will get a relation between k and zeta and substitute this k and zeta relation in this expression. So, you will get the relation for zeta, and that zeta equal to 0.998, and you know that zeta equal to C by m equal to, you know this relation, C by m equal to 2 zeta omega n. So, after knowing k and already you know the value of m. So, root over k by m will give you omega n, and after getting omega n you can find zeta, already you found zeta. So, omega n zeta are known to you. So, C by m equal to 2 zeta omega n, or you can find C equal to 2 m zeta omega n. So, using this relation C equal to 2 m zeta omega n, you can find the value of C, or this is the equivalent damping of the system, and K is the equivalent stiffness of the system. So, in this case you have seen that we have taken a compressor, and that compressor we have modeled it as a single degree of freedom spring mass damper system. We have taken the mass of the compressor and we have found the equivalent damping C and equivalent spring constant of the system. So, when the system is subjected to a force other than this f0 sin omega t, let us take a system when it is subjected to some other type of force. So, let I am applying a force of f0 cos omega t. So, this is the mass and this is k and this is c. Let me apply a force of f0 cos omega t. So, when I have applied a force of f0 sin omega t, if you have observed that force polygon, you can note or you just see this thing. So, this is the spring force k x I have taken. So, this is the damping force C omega x, and this is the m omega square x, this is the inertia force taken for this system, and this is the force, that is the applied force for this system. So, applied force f0 of the system. So, in this case you can observe that if I will draw a line, draw a vertical and horizontal line. So, this reference line is the horizontal line and I will draw a vertical line also. So, this is the x, and you can see this angle is phi and this angle is omega t minus phi. So, you can see that k x, so the vertical component of this k x equal to k x sin omega t minus phi. Similarly, the vertical component of the damping force will be equal to C x dot and the inertia force. So, you can see that the vertical component. So, when you are applying a force of sin omega t, so we are taking the vertical component, or the forces are represented by the vertical component of these forces shown in this graphical method. So, when a force of f0 sin cos omega t will act instead of a force of sin omega t, you can take the horizontal component of this force. So, the equation will remain unchanged and the same expression you will get for the response, and the response will be written like this. So, your response will be x will be equal to x, instead of sin you can write it is equal to x cos omega t minus phi. So, you can get same amplitude of response and same phase angle when you are applying a force of f cos omega t instead of a force of f sin omega t. So, as we are taking a linear system, so as this is a linear system, when instead of applying a single force, so if we are applying a number of forces on the system, so let a force, so this is the system and I am applying a force. So, let a number of force or this force which I can write as f1 sin omega 1 t plus f2 sin omega 2 t plus fn sin omega n t, or some force which, or I can write some force f p which is acting at a time sin, let it is omega t plus or minus phi minus some other angle psi 1. So, I can find the response by finding the response due to these individual forces. So, I can first find what is the response due to the force F 1 sin omega 1 t, then I can find what is the response due to this force F 2 sin omega 2 t. So, in this case this x 1 can be written as F 1 by k root over 1 minus r 1 square whole square plus 2 zeta r 1 square, and this phi 1 I can write that will be equal to tan inverse, this is 2 zeta r 1 by 1 minus r 1 square. So, for the first force I can write the response equal to x 1 sin. So, for the first force the response is x 1 sin omega 1 t minus phi 1. Similarly, for the second force it will be x 2 sin omega 2 t minus phi 2, and for the nth force, so x, so I can write this x as different component. So, I can write this x equal to x 1 plus, so I can write this x equal to x 1 plus x 2 plus x 3, x 2 plus x 3 plus x n, and for this I can write, so this x 1 you can write this x 1 equal to x 1 sin omega 1 t minus phi 1. Similarly, x 2 will be equal to capital X 2 sin omega 2 minus phi 2, and x n equal to capital X n sin omega n t minus phi n. So, for this what really this represents, this omega t minus psi 1 represent a force is acting on the system with an phase angle of psi 1. So, the response also will be, then the response will be led by an angle phi, another angle psi 2 I can write. So, due to this the response will be, let I am writing this response equal to x p. So, this x p will be equal to capital X p sin omega t minus phi minus psi 1 minus psi 1 minus phi p minus psi 1 minus phi p. So, where this x p is given by, so I can write this expression for x p, this is equal to f by f 0 by k or f b by k root over 1 minus, so root over 1 minus r p square, 1 minus r p square whole square, 1 minus r p square whole square plus 2 zeta r p whole square. So, where r p equal to omega by omega n, and this phi p equal to tan inverse 2 zeta r by 1 minus 2 zeta r p by 1 minus r p square. So, in this way when we have a number of forces acting on the system, then we can find the response of the system by finding the response of individual forces and then adding these forces. So, this is known as superposition principle. So, using superposition principle, we can find the response when a number of forces are acting on the system. So, today class we have studied about a graphical method by using which we can get the response of the system. Also, we have studied the magnification factor, and in this graphical method I have taken the force polygon by drawing the forces, the spring forces, damping forces and the inertia force, and I have found the response of the system by drawing a line parallel to this damping force and forming a right hand triangle. So, in this right hand triangle I got this square plus this square equal to 4 square. So, I got the response of the system. So, I got the expression for the response of the system like x equal to f0 by k root over 1 minus r square whole square plus 2 zeta r square. Also I got the phase angle. So, in this class you learn about the magnification factor, and also you learn about the superposition theory. By applying the superposition theory, you can obtain the response of the system for a number of forces when acting on the system. Also we have solved 2 examples, and in the next class I will tell you some alternative method to solve this differential equation of motion.